So example 424 says to solve the recurrence an equals the opposite of an minus 2 with initial conditions a0 equals 0 and a1 equals 1. Now, you might just glance at that one and solve it. It's a second order recurrence. A0 is 0, which means A2, and any even indexed A is going to be 0, and A1 and all the odd indexed A's are going to flip between 1 and -1. But we can do this. We can actually solve this still with our characteristic equation. So our characteristic equation is going to be x squared plus 1 equals 0. And the roots of this are, of course, x equals plus or minus I. Not terribly useful as it's stated there. Let's see, what can we do? We can set this up then as an equals lambda, I've been using c, c1 I to the n plus c2 minus I to the n. So with that in mind, we want a0 to be equal to 0. A0 is equal to c1 plus c2. We want a1 to be equal to 1. A1 is c1i minus c2i. So that says that c1 minus c2 equals, what's that going to be? Negative I, right, in order to make that multiplication happen. So that gives us that, let's see, c1 equals minus I over 2, and c2 equals I over 2. Just so you know, I'm going to town here. I have no idea at this point. I'm not seeing how it's going to come back up to what we were just talking about at the beginning. I have totally forgotten this example. I think it's going to work out. I'm starting to maybe catch a glimmer of hope here. So this says that an equals minus I over 2 times I to the n plus I over 2 times negative I to the n. This is, let's see, this is equal to, we are so close here, -1 plus -1 to the n, all right, times I to the n plus 1, that's negative from here, plus I to the n plus 1, that's from multiplying that in, over 2. So let's see what we can get here. If n is even, then this is 0. And if n is odd, then that is 2. And if n is odd, oh, this is positive. I already pulled that negative out right here. Okay, that's much better now. Yeah, so if n is odd, this is 2. So we get 2 times let's see. Nope, I did something wrong. I'm getting too many 2's. Let's see. Negative 1 over I. 1 over I is equal to minus I. Did I get it off by a factor of I? So let's see, you said this equation here. Yeah, so let me write that. C1 minus C2 times I equals 1. So C1 minus C2 equals 1 over I, right? Which is equal to negative I. So that one's all right. This is close, but I have a mistake somewhere in them. Oh, it's right here. I don't have a plus here anymore. Let me just, I'm going to take and pick this up on the next page. I factored it out. I used the distributive property, but then I left the plus in there. So I have an equals negative I over 2 times I to the n plus I over 2 times negative I to the n. Let me do that a little more carefully so I don't mess it up. So this is negative 1 times I to the n plus 1 over 2. This is plus then negative 1 to the n times I to the n plus 1 over 2. So those are the same. And so I get negative 1 plus negative 1 to the n, I to the n plus 1 over 2. So now this is equal to 0 if n is even. And let's see, if n is odd, then that's a 2 divided by 2, so it's just I to the n plus 1. So plugging that in, I mean, just to get a few, we get A0 is A2 is A4, and so on. All of those are 0. And A1 is I squared, which is negative 1. Is that what we had? No, we had that A1 was 1. What in the world did I do? May have been in finding my C1 and C2. Well, this is close. Does close count? Let's see. Negative I over 2 minus I over 2 is negative I, so that's okay. No, those look right. Anyone have any ideas? Because I ended up getting just the opposite of what I was looking for. And it would be right. If Alex is right up there, then that's right. But I'm pretty sure C1 minus C2 is negative I. Because negative I times I is 1. Well, that doesn't inspire a lot of confidence, does it? I'm not gonna, okay, hold on. What's Jonathan got? Maybe when I factored before distributing. So we have this here. I just factored out a -1. I factored out a -1 to the n. Kind of weirdly enough, well, but Chris, I think that might, I'm gonna play with it just a little. What I did, I don't think is wrong. I just multiplied the I and got an extra, an I to the n plus 1. But what if I had pulled an I out instead? Then that would be an equals. So if I take an I out, then that's a -1. So then that would just be a +1, I to the n minus 1 over 2. And this would be -1 to the n minus 1 times I to the n minus 1 over 2. And then if I factor that out, I get 1 plus -1 to the n minus 1 times I to the n minus 1 over 2. And so if n is even, then this is still 0. But if n is odd, then this is I to the n minus 1, which is just the opposite of what I had up there. And because I to the n plus 1 and I to the n minus 1 aren't going to be the same, they're going to be opposites of each other. And so this would give me A1 equals 1 and A3 equals -1. Which means that this is the right way to proceed, and that likely I made some little mistake in there when I took the I to the inside. I'm not seeing what it is though. And I think at this point, I'm just going to say this one matches our expectations. So we'll go this way. And I'll take a look at that later and see if I can figure out what went wrong. I told you I'd forgotten that recurrence. So let's see. By the way, though, and I'm not saying this by way of excusing getting the answer wrong, but rechecking your initial conditions. Arib says it's negative. Oh, you know what? I think that's what it is. When n is odd, this is a -2. That's right. So then that would make it all work out either way. Thanks, Arib. All right. So let's take a look at 425. So we have the recurrence Cn equals 9Cn minus 1 minus 15Cn minus 2 plus 7Cn minus 3. So this has characteristic equation. What's that going to be? X cubed minus 9x squared plus 15x minus 7 equals 0. All right, we're going to have to factor by grouping, I think, or maybe just guessing. Let's see, x equals 1 as a root. You can just plug it in and see real quick. So then when I divide by x minus 1, we get x squared minus 8x plus 7 equals 0. So that's x minus 1, x minus 7, and then another x minus 1. So we've got a repeated root of 1, and we've got a 7. So we have that Cn equals, ooh, need a new constant. I don't want to use C now for a constant. Let's use alpha. Why not? So alpha 1 times 1 to the n plus alpha 2n times 1 to the n plus alpha 3 times 7 to the n. And our initial conditions on this guy are C0 equals 0, C1 equals 1, and C2 equals 2. So C0 equals alpha 1 plus alpha 3, and that's equal to 0. C1 is alpha 1 plus alpha 2 plus 7 alpha 3 equals 1. And C2 is, let's see, alpha 1 plus 2 alpha 2 plus, good heavens, 49 alpha 3 equals 1. So that's a 3-by-3 system, which you can solve any way you like. I don't have the answer handy here, and I'm not going to spend a bunch of time doing the arithmetic. Probably throwing it in a matrix and row reducing it is pretty quick, especially since you've got a 0 already in that top position. You've got a nice line for your alpha 1s there. Let me see. Actually, hang on just a second. I might have this written down handy. Somewhat handy anyway. Not this one, it looks like. Why is alpha 2 multiplied by? Oh, you're right. Hold on. First, let's see. Courtney is correct. That should have been a 2. I just started writing the same thing. And then Nicholas asks, why is alpha 2 multiplied by n? And this is because we have a repeated root from our characteristic equation. So this is, let's see, theorem 422 in the notes. If you have a repeated root, if it's repeated 2 times, then you get a to the n and na to the n. If it's repeated 3 times, you would also get an n squared a to the n, or whatever your particular sequence letter is. That's in order, because just saying that 1 to the n and 1 to the n, that wouldn't give us anything new, and it turns out that multiplying by n actually works if you have a repeated root. Any other questions about 424, 425? All right. In that case, we're going to move on to 6.3. 6.3 is solving recurrences with ordinary generating functions. So I'm going to start with one that is simple, that we've actually done other ways, because we already know the solution to this, so we can check ourselves. The first thing that you probably want to do, it's not strictly speaking necessary, but if you want like a one way to do it every time, is to rewrite your, sorry, I need a S0 equals 0 there, is to rewrite your recurrence so that it's sk plus 1 equals sk plus k plus 1. And what we've done there is we've just made sure we don't have any k minus anythings. So that way we're always counting from k up. And that will just help us when we're trying to manipulate the sums. Because what we're going to do is we're going to let s of x equal the generating function for our sequence, the ordinary generating function for our sequence. And then we are going to multiply through by x to the k and sum from k from 0 to infinity, sum over the k's, so that we have our recurrence rewritten in terms of generating functions, or at least almost. So if I take this and I say sk plus 1 times x to the k, summed as k goes from 0 to infinity, equals the sum as k goes from 0 to infinity of sk, plus the sum, sorry, x to the k, plus the sum as k goes from 0 to infinity of k plus 1. Just a natural question that you might ask is, why can we do this? Well, think about it this way. I just took the recurrence and multiplied it by x to the k. Oops, almost. Keep wanting to forget that part. Multiplied every term in the recurrence by x to the k, which means I just multiplied both sides of an equation by something which is equal. And then I said, okay, but this recurrence is true for so long as k, this one here, so long as k is 0 or higher, this recurrence is true. We still have that same initial condition. This is another reason why it's helpful if our recurrence only counts our k and up, because then our initial condition at 0 is the k equals 0 case. So we know this is true, so S1 equals S0 plus 1. We know S2 equals S1 plus 2, and so on. So what we've done is we've taken all of those equations and just summed them infinitely, all of them. So of course, right now this just says like infinity equals infinity, perhaps, maybe not. Depends on what x is. But we've taken really just a linear combination of both sides of our equation. We multiplied both sides of our equation by the same thing and then added up all the versions of our equation. When we do that, you'll see that we get generating functions. Well, each of these is a generating function, but at least one of them here is the generating function we've already named. Our next goal is to get as many of these in terms of our named generating function as possible. I'm just going to leave this guy alone for now because he does not have our sequence in there. So this is really close. If I make this 1 over x times the sum as k goes from 0 to infinity, s of k plus 1, x to the k plus 1, and then re-index my sum, so I get the sum. You know what, let me work. It's all right. I'm just going to pause this right here because this is all right for now. The sum as k goes from 0 to infinity, sorry, k goes from 1 to infinity of sk x to the k, just by re-indexing, then that is almost equal. This is almost equal to that. The only difference is this is S of x, except it's missing the S0 term. Now, our S0 term is 0, so it wasn't actually missing anything. But in general, that's what we need to do. So let me go ahead and carry down my left-hand side here. This is equal to S of x plus the sum as k goes from 0 to infinity of k plus 1 x to the k. So normally when I do these, I work the left-hand side and right-hand side separately. I find that it just helps keep things straight. But this is the point where I'd put them back together anyway, so there wasn't a lot going on in this one. So let me write this out. 1 over x, s of x minus 0 equals s of x plus the sum as k goes from 0 to infinity, k plus 1, x to the k. This is actually a generating function that we know quite a lot about, right? That's one of our common ones. So maybe I should have done that on that step. Let me go ahead and quickly do that. So that one right there, that is the generating function for, which one? It is, this one is 1 over 1 minus x squared. So let me get that up on the top of the screen here. So from there, we can solve, and we should solve, for our generating function s. Remember, that's the generating function of the recurrence, of the sequence that satisfies our recurrence. So we want to find this. So this is 1 over x times s of x minus s of x equals 1 over 1 minus x squared. So this is 1 minus x times s of x equals x over 1 minus x squared. Almost there. We get s of x equals x over 1 minus x cubed. If we go back through real quick, remember 1 over 1 minus x is the sum of x to the k, and 1 over 1 minus x squared is the sum of k plus 1. We just use this one, x to the k. All of these k's start at 0. And then if I take the derivative of this again, I get 2 over 1 minus x quantity cubed, and that's the sum of k plus 2, k plus 1 over 2 x to the k as k goes from 0 to infinity. We've done all these before, but it's been a couple of weeks. And so then if I, terribly sorry, there's no over 2 here, that's from the next step. We just take the derivative again. So then x over 1 minus x cubed, I need to multiply both sides by x, I need to divide both sides by 2. So this is the sum as k goes from 0 to infinity of k plus 2, k plus 1, x to the k plus 1 over 2. And so then if I just re-index that, I get that x over 1 minus x cubed is equal to the sum as k goes from, let's see, say k goes from 1 to infinity of k plus 1 times k over 2, x to the k. And it doesn't actually change anything if I just start k at 0, right? So then that's k plus 1 times k over 2, x to the k. So our s of x is equal to that generating function, which has this form, this infinite sum form. So that means that sk must be equal to k times k plus 1 over 2, which is exactly what we would expect. Remember, we were solving this recurrence, and so that is, of course, equal to sk is equal to the sum as j goes from 0 to k of j, which is equal to k times k plus 1 over 2. So that one, it could have been done much more easily without generating functions, but it illustrates how the generating functions work fairly well. So what if we need some steps for this? We have a recurrence, a recurrence for a sub n, and it's written out. So then we rewrite. So lowest index is n, or k, or whichever letter you use. First we let a of x be the generating function for our unknown sequence. Then we multiply both sides of the recurrence by x to the n and sum. Then we rewrite in terms of a of x and other generating functions. Solve for a of x. And then finally, use generating function of a of x to find little an. So that's kind of an overview of the steps. We want to start our sum. Start your sum at the lowest index of your initial conditions. That's the other thing. Most of the time in here, we're going to start it at 0, but occasionally our first initial condition will be like a1, and so then you would just start summing at 1, and you would make your definition n equals 1 to, the sum as n goes from 1 to infinity, and you'd sum everything from 1 to infinity instead of worrying about 0. And that will make that step, where did it go? This step here, where you might have a sum that's a little off, then we can subtract our first initial condition, and we're not left trying to subtract something we don't know. I don't think I have an example of one of those in today's lecture, but we might get one on Monday. I do know you have one in the homework. So let's do a different example. Similar, if we start with sk plus 1 equals sk plus r times s0. So we don't know what our initial condition is, but our answer is going to be based on our initial condition. So we've just said S0 is S0. So then we will first let cap S of X, and I like to use the same letters here. You don't have to. You could use a G if you prefer. Cap S of X equal the sum as K goes from 0 to infinity of Sk X to the K. All right, and so now we want to take our recurrence. We want to multiply through by X to the K and sum. So this is the sum as K goes from 0 to infinity of Sk plus 1 X to the K equals, that's just S of X. So I'm going to go ahead and just write that, plus the sum of RS0 X to the K as K goes from 0 to infinity. Now, I told you I was going to work my left-hand side and right-hand side separately, so let's do that. The left-hand side here is equal to the sum as K goes from 1 to infinity. Let me do that way. So that's 1 over X times that sum, Sk X to the K. I did a lot in one go there, but you're going to get really used to that guy, Sk plus 1. When you throw it into the generating function, you're going to get 1 over X times S of X minus S0. It's an X, not a lambda. And my right-hand side is already equal to S of X there, plus RS0 just come out, and that's 1 over 1 minus X. So putting that back together, we have 1 over X times S of X minus S0. I can't zero that out this time because I don't know what it is, equals S of X plus RS0 over 1 minus X. So multiplying the X to the other side, we get S of X minus S0 equals X S of X plus RSO X over 1 minus X. Solving for S of X, we get 1 minus X S of X equals RSO X over 1 minus X plus SO. So then we get S of X, finally an expression for our generating function that doesn't depend on other parts of the generating function. We get RSO X over 1 minus X squared plus SO over 1 minus X. So now we want to try to use the generating functions for these expressions to figure out how S of X can be written as a neat little sum. So this is equal to, that's just an extra X times our usual K plus 1 X to the K. So that is RS0 times X times the sum as K goes from 0 to infinity of K plus 1 X to the K, plus this is just S0 times the sum as K goes from 0 to infinity X to the K. Our goal is to get S of X written as a single generating function, and so we're really there at this point. We could just combine them as is, but I really want to bring that X inside here first. So let's do RS0 equals the sum as K goes from 0 to infinity of K plus 1 X to the K plus 1. This is still the same. Now I can re-index that. I could re-index it to start at 1, and then that's K X to the K but then including the 0 term doesn't change anything because when k is 0, that's 0, so I'm just adding 0. Plus S0 times the sum as k goes from 0 to infinity, x to the k. Now I can write this as a single summation. I'm going to bring everything to the inside here. I get R S0k plus S0 times x to the k. Oh, just off the bottom of the screen, that's not useful. So R S0k plus S0, this has to be my sequence, right? This is my generating function. So this has to be sk. Sk equals, let's write that just a little nicer, S0 times 1 plus R k and that is the simple interest formula, actually. That's what that recurrence was for. Let's see, what's next? How about, since we did simple interest, what if we do, oh, sure. Let's see, which one did I? So you're talking about like the leap from that step to that step, right? Okay, so just separating that out, if we have the sum as k goes from 0 to infinity of k plus 1, x to the k plus 1, we could let j equal k plus 1. Then that would be the sum as j goes from 1 to infinity of j x to the j. Oh, sure. So if we let j be k plus 1, then when k is 0, j is 1, and so on. So the sum just goes from 1 to infinity. K plus 1 becomes j in both instances. Now, let k equal j. It doesn't really matter what we call it. So then that's the sum as k goes from 1 to infinity of k, x to the k. And so we just normally skip this step and we let k equal k plus 1, or let k replace k plus 1. And then the other thing that I did in that leap was I said, well, this is actually directly equal to the sum as k goes from 0 to infinity of k x to the k, because when k is 0, this is 0, so it didn't actually add anything. I did do two things in the same step there, but only because we had done that k plus 1 x to the k a couple of times. Being able to manipulate and reindex the sums, that's probably the most important skill you can have for doing this kind of problem. So, develop it. I'm not expecting it to be there right from the beginning, but work on developing it throughout the rest of the semester. So let's see, what if we did compound interest? Let's say sk plus 1 is equal to 1 plus r times sk, and we'll just say S0 equals S0 here. I know that's kind of lame, but we'll get an answer in terms of S0 instead of having a specific initial condition. So then first thing we do is let S of x be equal to the sum of sk, x to the k, as k goes from 0 to infinity. And then we're going to take and sum this sequence. So we take the sum of sk plus 1, x to the k, as k goes from 0 to infinity. And that's equal to the sum as k goes from 0 to infinity of 1 plus r sk x to the k. So my left-hand side, this is the same one I've been dealing with for a bit. So this is just 1 over x times s of x minus s0. And my right-hand side, that 1 plus r is just a constant multiple. So this is 1 plus r times s of x. Putting those back together, I'm going to go ahead and multiply the x across. When I do, I get s of x minus s0 equals 1 plus r times x s of x. So we get s of x times 1 minus 1 plus r x equals s0 when we rearrange. That should be a little less, just pretend. And so s of x equals s0 over 1 minus 1 plus r x. We can throw that into the geometric progression and get that this is equal to s0 times the sum as k goes from 0 to infinity of 1 plus r to the k, x to the k, which tells me that sk equals s0 times 1 plus r to the k. Compound interest formula. I think that's a good place to stop for today. Any other questions? All right, I'm going to go ahead and